Good morning, everyone. Thank you for joining us this morning for this webinar on mass move operations. We'll just do our usual and go straight into it. And if you have any questions, you can put them into the panel at any point and we'll get to them at the end.
Hello and welcome to today's webinar. Today we're going to be looking at what a masked move operation is in Cscape. Let's get started. Let's look at our agenda for today. We'll start by looking at what a masked move is, then we'll look at bitwise operations. We'll talk about the types of applications where you would use a masked move function and how you would code it in register-based advanced ladder. We'll look at doing a mask move using a user-defined function block in variable-based advanced ladder. There'll be demonstrations throughout, and we'll finish with a Q&A session. A masked move operation is a move function which selectively overrides a portion of a variable while leaving the rest unchanged. In a move function, data is transferred from a source to a destination. With a masked move, only a specific portion of the data is moved, overwriting a corresponding section of the destination. Masked moves are classified as bitwise operations, which operate on variables bit by bit. Bitwise operations are commonly used to parse data, dividing a chunk of data into multiple variables, or for packing data, combining multiple pieces of data into a single variable or data stream. There are many applications where these functions are useful. For example, CAN-open and J1939 communications, satellite and cellular communications, Modbus, barcode reading, RFID data and lighting control with sequencing. The common requirement in all these applications is the efficient packing of data in the smallest possible packet size, typically over a network. We can achieve this through masked moves and bitwise operations. We'll quickly review bitwise operations. They are instructions in Cscape that operate on the bits patterns of variables or registers. These operations work bit by bit and are commonly used to parse or mask specific parts of a variable. This allows us to extract and move a portion of the variable into another storage location. Now we'll look at a real-world example using register-based advanced ladder programming. Although the process is similar for both register and variable, we'll focus on a register-based example. So if we say we have a variable and it's stored in %or1, which contains integer data obtained from a third-party Modbus device. Within these 16 bits of data, there are 8 specific bits that are significant to us. In our example, these 8 bits are located in the middle, not the lower or upper 8 bits. We want to separate this data and store it as a distinct piece of information. To achieve this, we will utilize two bitwise operations, AND and SHIFT. First, we will apply the AND function, followed by the SHIFT function. Now we'll go into more detail on these operations. We'll begin with the AND function. Its primary purpose is to mask off irrelevant bits from a variable. In our example, we have 16 bits displayed in yellow and red, with the red bits being the ones we're interested in. Here's how the AND function operates. You take a variable and add it with a Boolean value which is converted to decimal in Cscape. This value represents a specific bit pattern. In the case of creating a mask, every 1 in the mask value preserves the corresponding bit, while every 0 turns the bit into 0 and disregards it. In our example, we would assign 0s to the yellow X's positions and 1s to the red N positions. Then, the resulting pattern would consist of 4 zeros at the top, 4 zeros at the bottom, and 8 ones in the middle. Performing the AND function would retrieve the desired data from the middle. Here we have the original register at the top and the data mask with the described pattern. Converting the binary pattern to decimal, we obtain 4080 in this specific example. By performing the AND function, we retrieve the desired data, which consists of the 8 bits in the middle. However, we're not finished yet. The issue is that the returned data is not correctly sized. It is shifted 4 positions higher, making it 16 times larger than the desired value. To address this, we simply need to perform a right shift by 4 positions to adjust the data to the desired position. By utilizing bitwise operations such as AND and shift, we can reliably extract the specific portion of data we need from a larger word. This approach is effective for data extraction as demonstrated. However, it may not work as well for data injection. For instance, if we were extracting speed feedback data ranging from 0 to 255 and we needed to write data to control the speed, the previous and shift operations would not be suitable. Now we encounter a similar situation. Our objective is to write a speed command to a drive using a different register number to store the speed setting. Let's assume it's an 8-bit value ranging from 0 to 255, stored in register 111. Our task is to pack this data into register 101 and transmit it to the drive. Below you can observe that we aim to position the speed setting, represented by SS, in the 8 middle bits of register 101. The bitwise operation shift left followed by a bitwise AND function cannot be used in this case. The AND, OR and XOR functions are unable to selectively write to specific bits of the destination. Consequently, the result would contain the speed data in the center as intended. However, the 4 bits at the top and bottom would all become zeros since the AND function writes to every position and cannot ignore specific bits. Here, the masked move allows us to specify a mask. This mask indicates which positions should receive data, ones in the mask, and which positions should be ignored, zeros in the mask. Consequently, we achieve the desired result of having the speed data in the middle without affecting the 4 bits at the top or bottom. By setting the mask to only write to the middle 8 bits, we ensure that the remaining bits remain untouched. In summary, the masked move is a useful operation that serves its purpose in scenarios where bitwise operations fall short, especially when it comes to injecting data. So, how do we perform a masked move in Cscape? While Cscape lacks a dedicated masked move instruction, it does provide the capability to access individual bits within variables. This feature proves highly beneficial, particularly in register-based and variable-based logic. By employing Boolean logic, we can selectively copy bits from one variable to another, specifying the source and destination bit numbers. In Cscape, to achieve this, especially in the traditional register-based approach without utilizing user-defined function blocks, we create a separate rung of logic with a coil and a contact for each bit we intend to write from a source to a destination. In our example, where we wrote 8 bits, this translates to 8 rungs of logic. Although not overly complex, it does require a few simple rungs of logic to accomplish the task effectively. The advantages of this approach are its straightforwardness and flexibility. It allows us to move a bit from any variable to another variable, regardless of their positions. While it may require some initial familiarity, it is not a difficult task. However, there are a few disadvantages to consider. Moving a large amount of data can become tedious, as each bit requires its own rung of logic. Additionally, in variable-based advanced ladder, access to bits 17 to 32 is not available. This limitation affects double word variables when performing a masked move function, at least in Cscape 9.9. However, it's worth noting that Cscape 10 will include this capability. Now we'll look at a different approach. Instead of creating a rung of logic for each bit, we can utilize a user-defined function block instead. We have developed two UDFBs for this purpose, one for integers and another for double integers, word and double word. These UDFBs enable performing the masked move operation within a single rung. The advantages of using UDFBs include the ability to perform the operation in a single rung and the flexibility to use Boolean logic for moving a few bits if needed. Importing the UDFBs may take a few minutes, but it can be done without any significant disadvantages. Now we'll look at the masked move function block in Cscape. We'll open Cscape and take a look at the function block. In this example, we've used the mask move word UDFB, which can be found in the toolbox under UDFB. It's specifically designed for 16-bit data. For our demonstration, we'll consider a speed control case. We start with a 16-bit speed variable ranging from 0 to 255, which corresponds to the desired control range for our drive. First, we shift the data by 4 bits to align it correctly for the subsequent mask move operation. Next, we need to create a mask. This mask is a binary pattern where zeros indicate positions where no write operation should occur, and ones indicate positions where the write operations should take place. In our case, we need 4 zeros at the top, 8 ones in the middle, and 4 zeros at the bottom. This binary pattern, when converted to decimal, results in 4080. Therefore, we set our mask value to 4080. By using the masked move function block, we can achieve the desired data manipulation efficiently and accurately. So this is our user-defined function block for the demonstration. The first input is our speed data, shifted over 4 positions. The next input is the mask, represented by the value 4080. This can also be a constant instead of a variable. The following input and output represent the original variable where we want to write the data. The result of the mask move operation is effectively written to the same variable. After performing the mask move, we should have only the speed data written to the middle 8 bits, leaving the other bits unaffected. Now we'll have a benchtop demonstration to see how the process works. We have the speed value ranging from 0 to 255, with the binary pattern displayed for convenience. The goal is to transmit a word over the network with the middle 8 bits representing the speed while leaving the top and bottom 8 bits untouched. To achieve this, we can set a bit pattern that remains constant, regardless of the speed value. We'll try a speed value of 55, and as we can see, the bit pattern matches the speed successfully, without affecting the other bits. Now, before we move on to the double word version of the function block, we'll take a quick look at the logic inside this user-defined function block. Although this step is optional, it provides insight into how we created the user-defined function block. We can take any bit from any variable and write it to any bit in another variable. What's different with this function block is we can address any of the 16 bits that need to be written. For each output bit, of which there are 16, we have a single coil, and we either write a 1 or a 0. If the incoming mask for that bit is 1, we copy the corresponding bit from the first input. If the mask is 0, we preserve the output bit without modification, passing the value from the second input. We repeat this process for all 16 bits in the word. The logic is straightforward and provides an efficient solution for tasks involving bit packing and similar operations. Now we'll have the dword demo to see how it works. This time we'll use the same example, but everything will be twice as long. We have a 32-bit D word where we need to pack the middle 16 bits of data, disregarding the lower and upper 8 bits. Although we're placing the data in the middle for both examples, it's important to note that the mask move function works wherever you need it. Similar to the previous demonstration, we take our speed data, which now ranges from 0 to 65,535, and shift it by 8 bits according to our example. The mask for this case is larger, consisting of 8 zeros at the top, 16 ones in the center, and 8 zeros at the bottom. It's also worth mentioning that this UDFB operates on 32-bit variables instead of the previous 16-bit ones, allowing for the same functionality with double integer or word type variables. Now we'll go back to the bench for a quick demonstration. Firstly, we'll load the double word program, which loads quickly because of removable media. Now this example is similar, but for double word programs. The desired value, speed, remains in the middle, while the bit patterns for the top and bottom 8 bits are fixed to ensure they remain unchanged. As we adjust the speed, no changes occur at either end. Even when we push the value up to 50,000, the top and bottom bits remain unchanged. It works well and is also simple to use. Now, before we conclude, we'll take a closer look at the logic inside this function block. While the first 16 bits follow the same pattern as before, we need to employ a clever technique for the upper 16 bits. In variable-based advanced ladder, access to bits 17 to 32 in a 32-bit variable is restricted. To overcome this limitation, we perform a 16-position rotation on all 4 variables: the 2 inputs, the mask, and the output. This rotation effectively moves the previous top bits to the bottom, while the bits we just wrote and the preceding 16 bits now reside at the top. This allows us to copy and paste the remaining 16 bits. Once completed, we perform another 16-position rotation to restore all bits to their original positions. However, executing a simple rung of logic and utilizing this user-defined function block renders this workaround unnecessary. With ease, we can select any 32 bits from a double word source and write them to the desired output variable. It's a straightforward and efficient process. In industrial communications, efficient packing of communication packets, whether for cellular, satellite, or lighting sequencing, is crucial. Standard move functions and bitwise operations often write the entire variable, be it a byte, word, or double word, potentially overwriting unintended data. However, a masked move instruction selectively writes to specified bits while leaving the rest unchanged. This ensures precise data manipulation without the risk of inadvertently altering important information. So that concludes today's webinar. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, nice and straightforward. Okay, I don't see anything in at the moment. So next week we do have string handling with UDFBs. As usual, the registration link is there for that, as well as our next 2 webinars taking us up to the start of August. Okay, failing that, thank you all for joining this morning, and we hope to see you again next week. Have a good day.